Okay, hi everyone, welcome back to the Comptia Security Plus course, Public Key Infrastructure. A public key infrastructure, PKI, is an entire system of hardware and software policies and procedures and people. It is used to create, distribute, manage, store and revoke digital certificates. But if you have connected to a secure website in the past, you have been part of a PKI, but PKI can be used for other things as well, such as secure email, transmissions and secure connections to remote computers and remote networks. The PKI, just blow my nose, is all-encompassing. It includes users, client computers, servers, services, and most of all encryption. Don't confuse PKI with public key encryption, though they are related. PKI is a way of accomplishing public key encryption, but not all public key encryption schemes are PKI. PKI creates asymmetric key pairs, a public key and a private key. The private key is kept secret, whereas the public key can be distributed. If the key pair is generated at a server, it is considered to be centralized and the public key is distributed as needed. If the key pair is generated at a local computer, it is considered to be decentralized and the keys are not distributed. Instead, they are used by that local system. An example of public key usage will be a certificate obtained by a web browser during an encrypted session with an e-commerce website. An example of public key usage will be when a user needs to encrypt the digital signature of a private email. The difference is the level of confidentiality. The public key certificate obtained by the web browser is public and might be obtained by thousands of individuals. The private key used to encrypt the email is not to be shared with anyone. In a nutshell, public key infrastructures are set up in such a way as to bind public keys with user identities. This is usually done with certificates distributed by a certificate authority. Less commonly, it is done by means of a web of trust. Let's go ahead and describe these concepts in a little more detail. Certificates. Certificates are digitally signed electronic documents that bind a public key with a user identity. The identity information might include a person's name and organization or other details relevant to the user to whom the certificate is to be issued. Most certificates are based on the X509 standard, which is a common PKI standard developed by the ITU that often incorporates a single sign-on SSL authentication method. This way, a recipient of a single X.509 certificate has access to multiple resources, possibly in multiple locations. Although difficult, X.509 certificates that use MD5 and SHA1 hashes can be compromised. A more powerful hashing algorithm such as SH2 should be implemented with the certificate. X.509 is the core of the PKIX, which is the IETFS Public Key Infrastructure X.509 Working Group. Components of an X.509 certificate include the following: owner user information, including their public key; certificate authority information, including their name, digital signature, serial number, issues and expiration dates, and version. Certificates can be used for connections to websites, for email, and for many other things in the internet world, as well as encryption done locally. For example, a user working in a Windows environment might want to use the encryption file system EFS to encrypt data locally. The Windows domain can be configured to allow for user certificates, governing and enhancing this encryption process. So certificates can be used internally or externally, but most people are most familiar with the certificate used to make secure HTTP connections, usually with SSL TLS based certificates. We'll focus mostly on that type of certificate as we move forward. SSL certificate types. It's a good idea to classify certificates the way that companies that sell them do. This includes domain, organizational and extended validation certificates. Domain validation DV certificates are where the certificate authority checks the rights of the applicant to use a specific domain name. We'll discuss the term certificate authority CA later in the chapter, but for now, simply put, it is the entity that issues the certificate. Organizational validation OV certificates go beyond this by also conducting some vetting of the organization involved, the result of which is displayed to customers. Extended validation EV certificates go further by conducting a thorough vetting of the organization. Issuance of these certificates is strictly defined. Many companies have subdomains for the websites. For example, I own davidprowse.com. I might also opt to create subdomains such as tools.davidprowse.com and software.davidlprowse.com. Generally, if you connect to a secure website that uses subdomains, a single certificate will allow for connections to the main website and the subdomains. This is known as a wildcard certificate. For example, davidlprowse.com, meaning all subdomains of davidlprowse.com. Your organization might allow this, or for additional security might use a different certificate for each subdomain, possibly from different providers, but this can prove to be expensive. For small business and organizations, the single certificate is usually enough. In fact, if the provider allows it, a small organization can use a multi-domain certificate by modifying the subject alternative name SAN field. An organization can specify additional host names, domain names, IP addresses, and so on. Single-sided and dual-sided certificate. Most communication sessions, such as secure web sessions, use single-sided certificates. This is when the server validates itself to recipients of the certificate, such as users who are accessing the website. In these types of scenarios, users do not need to validate their own identity. This would be resource intensive, especially for a secure web server that might have thousands of concurrent connections. Sometimes an organization might choose to have the server and the user validate their identities. This would be using a dual-sided certificate. It works well when a limited number of computers and sessions are involved. When more computers are added to the mix, the amount of resources necessary might be a strain on the issuing CA. Certificate chain of trust. A certificate chain is a list of certificates that utilize a chain of trust concept. This is where each component of the system is validated from the bottom up in a certificate chain, also known as certification path. The anchor for this trust is the root certificate authority. At the bottom of the chain, we have the entity certificate for a machine computer. That's the certificate that you would see if you looked at the details of a secure HTTPS session in your web browser. That then handshakes with an intermediate certificate belonging to a subordinate security authority. This certificate signs the entity certificate. That then handshakes with the root certificate, which represents the root certificate authority. It signs the intermediate certificate, and in and of itself it is self-signing, which means that it not only creates a certificate but signs it as well. It signs it with its own private key. The root CA will employ code signing, digitally signing and timestamping the certificate to provide integrity and authenticity. However, even this can be defeated, so the main security admin has to always be on the lookout for CVEs detailing revoked certificates and even entire issuing certificate companies that may have been compromised. Certificate formats. There are several certificate formats you should know for the exam. They can be identified in part by the file extension or encoding type. First, let's briefly discuss the ITU TX.690 encoding formats. Basic encoding rules, BER. This is the original rule set governing the encoding of ASM.1 data structures. Any data created is encoded with a type identifier, a length description and contents value. BER can use one of several encoding methods. Canonical encoding rule, CER. This is a restricted version of BER in that it only allows the use of encoding types. All others are restricted. Distinguished encoding rules, DER. Another restricted variant of BER. This only allows for one type of encoding and has restrictive rules for length, character strings and how elements are sorted. It is widely used for X.509 certificates. For example, certificate enrollment in Windows servers use DER exclusively. Now let's briefly define the certificate formats and extensions you might encounter. PEM is a very common format that uses base 64 encoding ASCII files. It stands for Privacy Enhanced Electronic Mail and can be identified with the .PEM file extension, though the format might also use .CRT, for example Microsoft CER or key extensions. It uses the DER encoding method. If the certificates use a file extension different from .PEM, you can tell if it is a PEM by opening the file with a text editor and looking for the begin certificate and end certificate statements. However, if the certificate uses the .DER extension, then the certificate file is in binary form instead of ASCII. Because it is in binary, you will not see the begin and end certificate statements that are displayed in a .PEM. P12 PFX is a binary format based on PKCS #12 used to store a server certificate, intermediate certificates and a private key in only encryptable file. It is typically used to import and export certificates and private keys. You may see the .pfx and P12 extensions associated with PKCS #12 based files. .pfx stands for Personal Information Exchange and is used by Microsoft for release signing. The certificate and its private and public keys are stored in the .pfx file. A PFX file can also be developed by combining a private key with a PKCS #7 .p7b file, as might be done in Windows Internet Information Services IIS or P7b format. Certificates can be used by themselves in IIS as the basis for SMIME and single sign-on. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.